everyone. My name is Zhu. Currently, I'm a data scientist in Shopee, Singapore. So may I know, is there anyone do not know Shopee? So let's suppose everyone knows Shopee, okay. Okay, so I'm very glad to stand here to give the talk which is related to exploiting auxiliary information for better recommendation. So during this talk, I will follow this agenda. First, I will introduce some background of recommender system, and then I will introduce some recommendation method with auxiliary information, which include leverage, the set information of users or items, and then I will focus on the method with item set information. So both the two topics seems to has nothing to do with Python, right? But finally, we get the implementations by Python. At least we have something to do with Python. Okay. Compared with the previous talks, I think my talk is a little bit different because it's include a little bit much of the theoretical informations. But I will try my best to do not let you guys suffer a lot. Okay. So as you know, recommender system have become essential tools to help solve the information over the problems, to provide personalized recommendations for the customers. They have been widely applied into a lot of different application domains, like the e-commerce, travel, and point of interest, and multimedia. So in our Shopee context, recommendation is a key function of our platform. Every day we generate a lot of recommendations for your guests. Then you can search your favorite things faster. And then the most successful technique for recommendation is collaborative filtering. I suppose you guys have heard about that, okay? And then normally we use the user item historical interaction data. For example, like the users click the items or purchase the items, or the user gives some ratings to the items. We use those historical information data to predict the user's future interest. So basically there are two types of collaborative filtering method, user-based or item-based. The rationale behind is that similar users will have similar interests, and also from the item side, users may have interest to similar items. But traditional collaborative filtering method suffers from data sparsity and cold start problems. So what is data sparsity? That means most of the people only have a few interactions with the items. So also in our Shopee context, we have a huge number of items in our platform, but most of the users only have clicked or purchased a small number of products. So that is the data sparsity problem. And the cold start means there will be some new users or new items will come into our platform. To address those problems, researchers, they try to use the auxiliary information about the users or items to address the problems. So from the user side, a lot of user auxiliary information has been considered. For example, like the social networks and the trust informations. So they assume that the users will have similar interests with her trusted friends. And also from the item side, we consider the item categories, brand, and tags information. For example, let's say the customers in our Shopee. When a new customer into our platform, first we may leverage the user's profile to do some recommendations based on her gender, occupation, and so on. And once the user has some interactions with our items, then we can know the items category. Based on the category, we can recommend more items to the users. Until now, there are a lot of recommendation methods with auxiliary information being proposed in both academic and industry. But here in this talk, I only focus on the method with item auxiliary information. The first one is the category hierarchy. Here I put a figure to show the toy example of the category hierarchy. This is the hierarchy for women clothing in Amazon. So first, the women clothing is divided into some generalized categories like athletic clothing or fashion clothing, and then the athletic clothing is further divided into some localized categories like the athletic pants, shoes, and shirts. So suppose a customer, she prefers to, the athletic clothing, she buys some athletic pants. So she may, possibly to buy the athletic shoes to match with her pants. So that's kind of information could be, injected into the recommendation. And also with the development of semantic web, knowledge, more and more knowledge graph information from different domains are available now. Here is a figure to show the toy example of knowledge graph in the movie domain. So in this graph, we contain users, movies, actors, and directors, and runners as entities. And also the knowledge graph contains the entity relations, such as the users could rating the movies, and also the movies can belong to several different genres, and also the movies can be acted by some actors and it is directed by some directors. So such kind of information, they inject some prior knowledges and could be very useful to generate accurate recommendation. So based on the two types of structures, I will introduce two methods. Here I won't tell too much theoretical things. I'll just give you the high-level ideas. The first method is hierarchy-based. Actually, this method is proposed by me during my Ph.D. study, and this work has been published in some top-tier artificial intelligence conference. So this method is mainly to exploit both vertical and horizontal dimensions of category hierarchy. So the category hierarchy, contains a set of categories and their relations. But the category relations can be considered, in two dimensions. So first, in the vertical dimensions, let's see, the shirts, athletic clothing, and the women clothing, they have the affiliated two relationships in the vertical dimension. And so let's suppose, as I previously mentioned, the example, if a user, purchase some athletic pants, she may also purchase some athletic shoes to match her pants, because both the athletic pants and the shoes belongs to the athletic clothing. They inherit some characteristics from the athletic clothing. And also in the horizontal dimensions, the categories also have either alternative or complementary relations. Such kind of information relations can also be considered into recommendation. So let's suppose a customer prefers athletic clothing instead of the fashion clothing. So she will buy athletic shoes to match her athletic pants instead of the heels. So in this case, the athletic pants and the shoes, the two categories are complementary, but the athletic shoes and the high heels, they are alternative. So the method is mainly to incorporate to two types of category relations into two dimensions into the model. So here I will skip some of the formulas. Do not let you get suffer a lot. Okay. Here is a user item. Yeah, a lot of theoretical information is included here. I'm so sorry to let you get suffer a lot. Okay, so the U is the user, and I is the items, and the CI is the categories that the item I belongs to in the hierarchy. So we define the probability of item is rated by a user by the number of users who rated the item divided by the total number of users, and then we define the item co-occurrence. The co-occurrence equals to the probability that the two items are jointly purchased by the users divided by their respective probabilities. And also finally, we use the item co-occurrence to define the category influence in vertical dimension. So I won't explain the formulas too much. I just give you high-level ideas. So the category influence can be considered as the items that is characterized by the categories. And also for the horizontal dimensions, we first define the item relations as three types: alternative, complementary, or independent. And then we quantify the item relations by Bayesian inference and the conditional probabilities. We prove that if the two items are alternative, then the item co-occurrence value will be smaller than 1. And otherwise, if they are complementary, then the item co-occurrence will larger than 1. Then the category relation is also defined by the the relation of the items that are characterized by the categories. And then after that, we do some data analysis on the real-world data sets. We use the Amazon data set, and we find that in the vertical dimension, the categories at the different layers of the hierarchy indeed have different influence on the atoms, and also in the horizontal dimensions, there indeed have the complementary and alternative relationships between different categories. So based on this, we propose the model. Here is objective functions, a lot of formulas, sorry. I will try to simplify it. So the formula contains two parts. The first part is cost function, and the second part is regulator. So the first part is used to, the key point is the two parts. Both the two parts are very important. So the first part is to use adapt the item latent factors. Here, one thing I need to mention is that we use the latent factor model. I suppose you guys know what is the latent factor model, okay? And then theta is the latent factors for the users, items, categories. That means we project all the users and items and categories into a latent space. So theta U means the user's latent vector, and theta I means the atom latent vector. So here the theta I bar means the adaptive atom latent vector with consideration of the vertical category influence. And also the pi function means the regularizations with considering the category relations in the horizontal dimension. So let's see, an item is characterized by all its affiliated categories. Then the adapted item latent factors can be formulated in this vector. So the first term here, theta I is original, the item's original latent factor. And the second part is, is affiliated to category latent factors. That means an item's latent factor will be affected by itself and also is affiliated to category latent factors. From previous data analysis, we know that different categories may have different influence on the atoms. So we put a parameter vector here to learn the different influence of the categories at different layers of the hierarchy. And also for the horizontal dimensions, we devise regulators to control the distance of the category latent factors. If the two categories are alternative, that means their latent factors should be far away from each other. And if they are complementary, that means their latent factors should be close to each other. So based on this, we devise the regulators to constrain the distance between the category latent factors. And by carefully design, we can ensure that if the two categories are alternative, then the sigma fg is smaller than 0. Otherwise, if they are complementary, the value will be larger than 0. So after that, we test the effectiveness of the method on the Amazon datasets from 4 different domains: clothing, electronics, CD, and home kitchens. And we compare with several state-of-art recommendation methods. And the experimental results show that our method outperforms others. And also compare with the category hierarchy. Knowledge graph is the more complicated structures, which contains various types of information related to items into a unified space, which helps develop insights to recommendation problems. So here is what is knowledge graph. I have to say there is no formal definitions for knowledge graph. So it can be considered as some kind of graph-based knowledge representation, which include nodes and link. The nodes represent the entities, and the link represent the entity relations. So here, from this knowledge graph, we mean for users' preference towards items. Let's take Bob and saving price ring as an example. So we can infer Bob's interest towards saving price ring by the following paths. The first one is from Bob to the terminal and to drama and to saving price ring. The second path is from Bob to the terminal to Steven Spielberg and to saving price ring. So from the two paths, we may infer that Bob's may have much interest into the movies that belongs to drama or directed by Steven Spielberg. Okay, so the running example means that the different passes connecting a same entity pairs often carry relations of different semantics, and also the different paths have different importance in characterizing users' taste over items. So to achieve better exploration of knowledge graph, there should be a model not only capture the semantic of different passes, but also distinct the silence of different passes. Therefore, we propose a model. Here is the framework of the model. Seems a little bit complicated, but the model is composed of 3 modulars: semantic path mining, recurrent network batch, and silence determination. And the first part, semantic mining, path mining is used to automatically discover all the quality passes that connect the user and item pairs. And the second part is to encode the path with a batch of recurrent networks. And the third part is to a pooling layer to discriminate the importance of paths. Okay, so I will tell some details about different parts. The first part is semantic path mining. So as we know that because in the knowledge graph is very huge, it contains a lot of informations. So there are a lot of entity pairs. To improve the model efficiency, so we only select the user to item pairs because our goal is to recommend the items to users. And also, we only select the paths with some certain length constraint. That means because longer passes may introduce some remote neighbors, thus leading to some noises. So we just maybe select the path maybe with length smaller than 7 or 9 or something like this. Yeah. And this is the second modular's recurrent network batch. After the path mining, we have multiple passes that connecting a user and item pairs. And the passes have different lengths. So we use a batch of a recurrent neural network to encode the path. We have embedding layers to embed all the entities in the path. And then we use the attention-gated hidden layer to control the information flow. And the third part is the silence determination. This part, so in this part, because previously, we know that different paths may have different impacts on the user's taste over items. So here we add a pooling layer to select the important features. Finally, we use a fully connect layer to quantify the relations between the users and the items. Here is objective functions. We use banner cross entropy, and also we test the proposed method on the 2 data sets. One is movie length and one is yips. Another is yips. And the experiments show that our proposed method outperforms others. And here also, the only thing that related to Python is here. Yeah. So I also implement the final method in Python. I include 5 parts: auxiliary information mapping, data splitting, and negative sampling, path extraction, recurrent network, neural networks. So if you are interested in the paper, I also provided you guys links, and you can, I don't know whether you are interested. So let's go to the code here. Here is my GitHub. And here, because I would like to see I am not a talented programmer, so the code, the generalizability of the code is not so good, but at least it works. Yeah. Okay. So the running environment is Python 3, and I use PyTorch. So here are 2 data sets we consider: the movie length and yip. So in the movie length, we have the movie's auxiliary informations. Here is the data format. Here is the ID means the movie's ID, and also we have the genre informations of the movies, the director informations of the movies, and the actor informations of the movies. And for the yip data sets, we have the location ID and the location genre and the city of the locations and so on. So what we do is to map all the informations into ID, and then we split the data because we have to train our model and test our model. So this one is to, based on the time step, we split the data, the user movie rating data, into training and testing, and then we do some negative sampling to balance the model training process, and then we extract the paths from the knowledge graph. Finally, we put the passes into the recurrent network. So the code is here. I don't want to show more details about the code. If you are interested, you can search by yourself. So thanks for your attention. I'm so sorry to let you guys suffer a lot. Sorry.
So the algorithm that you have discussed so far is now used in Shopee.
Actually, to be honest, some of the, because in Shopee in industry we have to consider the time complexity, the usability and something like this. But the algorithms has not been fully employed in Shopee. But we have exploited some part of the the algorithms into our platform,
Yes.
and it works. Yeah.
Yes, it's quite nice to see those formulas and all of those.
Thank you.
Thank you for that.
I'm very glad to hear that.
And then also the performance of the recommender system is quite good because it outperforms the other algorithms.
Yeah.
Now I'm interested on the performance when you apply it to real application.
You mean in real application?
Yeah.
Because in our Shopee, but I have to say that the new algorithms that incorporate some parts of my algorithms, not all the all the part of my algorithms. Previously, we used the basic collaborative filtering without the auxiliary informations, and later we designed the new algorithms, and the CTR indeed improves. The CTR and the CR improves.
Yeah. Do you have you timed the execution of your algorithm with respect to generating the result for the recommendation?
Sorry?
Do you have timed your algorithm?
The time complexity, you mean?
Yeah. So how long will it take to have that kind of performance?
Because we just consider for the auxiliary informations, we also we just consider the category informations, so that won't increase the time complexity so much. Yeah.
Okay, thank you for that.
Okay, thank you. Thanks for your question.